And this is what I got, a bunch of stupid videos. So I put them on there anyway, and you know, you can enjoy them or not like them, you know, whatever you choose. Okay, so now we're going to talk, we're going to finish chapter 3 today. And today we're talking about lipids, proteins, and nucleic acids. And so, hopefully you'll have an idea of what these things are and be able to identify them all on the molecule sheet. So we're on page 42, 3.3. We're going to talk about lipids, or fats. Now, fats, lipids come in different types. There's fats like butter or lard. See, lard, that's kind of a funny word, isn't it? Lard. Those are fats, and that's like the fat that you cut off the meat off your steak, or that you get your mommy to cut off your steak because you don't like it. Just yucky. Oils, like cooking oils, if you've ever seen vegetable oil or something like that, or oil and vinegar salad dressing, those are lipids. Phospholipids are on the outsides of cells. I'll show you what those look like. Steroids are hormones that are created from fats. You probably look at me and you go, wow, he must be on steroids because I'm so big. But I'm not, it's natural. And I'll show you what those look like. And waxes have kind of a different look. But all of these are lipids, and lipids all have a couple things in common that I'm going to show you here. That's a walrus, and under his skin he's got lots of thick fat that insulate his body so he doesn't get cold when he's swimming around in the real cold waters up there near the North Pole. And they say that the fat underneath the skin is so thick and tough, it's like a tire, like on a car. It's like really dense and thick.
It's like stuff that they use on like CSI when they're shooting a gun.
Ballistic shell.
Bullet.
They use walrus fat?
No, it's that kind of.
Ballistic
It looks
gel.
like that kind
Oh,
of
it
stuff.
does? How do you know so much about walrus fat?
I don't know. That's what
He's
I'm
a walrus hunter.
assuming.
Oh, okay.
Brittany comes from a family of walrus hunters.
Brittany's a walrus.
Hey.
I'm joking.
She's cute.
Now,
She's part walrus.
a fat is basically made up of two. A fat is basically made up of two units. One is called a glycerol. And a glycerol consists of 3 carbon atoms joined together in a line with 3 hydroxide groups hanging off the edges. And I like to use this little magnet here to show what a glycerol looks like. 3 carbons and 3 hydroxides. Looks like a big letter E. Or a letter M. Or the number 3. Or the letter W.
So take your pick.
It's a lot of different things for that symbol.
Or
Now, the other thing are the fatty acids. Fatty acids are chains of carbons, many carbons in a row, with hydrogens connected to them. And at one end is a COOH group, which is also an acid group. If you remember yesterday's lecture, talking about the functional groups, when we talked about the acid group. It's also called a carboxyl group.
Is that like number 5 or number 3 on the sheet?
Probably is on your sheet.
Well,
Now, go ahead.
It's like actually it's not.
I don't want to refer to the sheet the
Okay.
rest of the lecture because I don't want you to do it for homework.
Okay.
But yeah, a lot of these that you're going to see are on the sheet. Okay? So kind of get it in your head what these things look like. But there's a fatty acid chain right there, a bunch of carbons and hydrogens. And if you just take these fatty acid chains and you stick them onto the glycerol, click,
Can they get that one?
click, there you've got a fat. That's what a fat is. That's what it looks like. It looks like a big letter E with long things sticking off of it.
he needs to cut his finger.
It's also called a triglyceride. Have you ever heard that? You might have heard that word before. You got to watch your triglycerides. They're talking about your fats. And there's tri meaning 3 fatty acid chains. glyceride referring to the glycerol. That's how you make a fat.
Uh-huh.
Now some fats have 3 tails, some fats only have 2, and some fats only have 1. But that's one thing you'll find in common. All fats have these fatty acid chains hanging off of them.
Have 3.
Not all of them have 3, but all of them have at least 1.
Could they
The
have,
most common form looks like this and has 3.
could it have 5 or 6?
No, you never find them with more than 3. Now, these long carbon chains, fats can be made from carbohydrates. If you take this ring of carbon atoms and you straighten it out, you can make it into a fatty acid chain. Your body can. It would take a carbohydrate ring, straighten it out, put a couple of them together, and you've got a fatty acid chain. So fat is the way your body stores sugars. If you eat a lot of sugar for breakfast, you're just going on those Rice Krispies and you just keep pouring sugar in there, you're not going to be able to burn up all that sugar immediately unless you're Michael Phelps or Tom Willis and you're just in the Olympics. I'm Tom Willis, that was a joke. The joke was comparing Michael Phelps to me. He's only about half the athlete I am. Anyway, what was I talking about? Anyway,
Carbohydrates.
if you eat a lot of sugar, you're not going to burn it right away. You're going to store it for later. And one way you can store it is to make it into fat. So if you eat a lot of sugar, you'll get fat. If you don't burn it up. If you do burn it up, you don't have to worry about it. Now, not these fatty acid tails, there are 2 types. Some fatty acid tails have all single bonds. If you look at this one, it's got all single bonds all the way through, except for the one at the end. And we don't really count the one at the end. So if it's got all single bonds, it's called a saturated fatty acid. This is where saturated fats come in, if you've ever heard of those. If it's got some double bonds in the tail, it's unsaturated fatty acid. And saturated fats are worse for you than unsaturated fats. Usually saturated fats are solids, and unsaturated fats are liquids, like oils.
Corn's
Well, corn produces corn oil, and corn oil is unsaturated fats. And milk produces butter, and butter is an example of a saturated fat.
Which is the worst fat, trans fat or saturated fat? Isn't it like
I'm not sure what trans fat is.
I don't know. I think it's like trans.
You don't need to know.
I don't know.
Wait, what are
No, it like clogs your
I don't even want them there.
Unsaturated are these that have double bonds.
Okay.
And the thing about unsaturated fats is they can't get too close to one another. Let me show you what the molecules, this is what the molecules actually look like. Here's saturated fats with all the single bonds. And their little legs, their little fatty acid chains are all straight. And you could imagine you could pile a lot of these close to one another. You could take one of these and set it right here, and another one and set it right here, and you can jam them all in real close together because they're nice and flat and straight.
Is that why they're solids?
That's why they're solids. These molecules you can't get very close together because they're all windy and wavy, and so they're liquids. And the saturated fats tend to hold more fat in a smaller amount of space, and so they're a little bit worse for you. Make you sensey?
Make you sensey. Make you mucho sensey.
Now, here we're looking at the membrane of a cell. And every cell in your body and every cell in the world has as its membrane fat molecules. And here they are. And these fat molecules only have 2 fatty acid chains instead of 3. They're called phospholipids. You ever heard of those before?
No.
Thinking back, you gotta think way back. When did y'all have life science?
Like 7th grade,
7th grade. That's
but-
a long time ago.
we never really did anything yet.
Here's the glycerol. Here's the 2 fatty acid tails instead of 3. And this one's unsaturated because it's got a double bond right there that makes it bend. And then you add a little phosphate onto the glycerol and you have what's called a phospholipid. Which we spent half a chapter talking about just phospholipids.
Awesome.
That's how important this molecule is.
Put it there.
Here's a steroid. Cholesterol is a steroid molecule. Have you heard of cholesterol before?
Yes.
And this you just have to kind of memorize the structure of. If you ever see a structure that looks like this, it's 3 hexagons and a pentagon with a fatty acid tail coming off the end. A single fatty acid tail. That's cholesterol, and that's a fat.
Always.
Well, if it's got the long tail coming off the end, it's cholesterol. If the tail has been removed, it's testosterone, which is the male sex hormone.
Wait, the tail's been removed, it's estrogen because it's HO and.
Or estrogen. Yeah, both testosterone and estrogen have had that long tail removed. Testosterone and estrogen are made from cholesterol.
Does the 2 lines in the estrogen thing mean it's double? Like the blue line?
Does, yeah, that means double bonds.
Okay.
Good question. So did you realize that your sex hormones are made from fat?
Do you know?
Women are not able to have children unless their fat levels are high enough, for one reason, because only then do they make enough estrogen to give birth to kids, to get pregnant.
And how did Nicole Richie get pregnant?
I don't know. Color of
She
the
was
nasty.
Yeah, she was like,
Normally, if you're real skinny, you stop having your period and you're not able to have kids. But I guess for different people, it can vary. So you just kind of got to memorize this structure. Cholesterol, testosterone, estrogen, they're all steroids, and they got that structure. And that's just something you got to memorize. Okay, that is a steroid. That is a fat. Some people would mix this up with this. Can you see how that could be mixed up?
Yes.
Yeah.
Okay. It could be. It can be. And you got to not mix it up somehow.
Wait, so those are lined up in a row and those are kind of connected by the...
And that one has a pentagon in it.
This would be a polypeptide. I mean, this would be a polysaccharide.
Oh yeah, because it's 6.
And this is a steroid.
It's got a pentagon, so it's a
It's
steroid.
got a pentagon in it. That's a good way to remember it. And it just has a different look. You'll never see a polysaccharide that looks like that.
Yeah.
This is a wax. If you look up close at the structure of a wax, it's got a fatty acid tail connected to a long chain alcohol. But it's just kind of like a very small connection between 2 long strips. I've never seen them ask you to identify a wax before on any test. Not the test I give and not on the AP test. So I doubt you would have to know this one.
This.
But you never know. It could pop up. I don't make the AP. I only make my test. I don't make the AP test. So they could show you that picture and say, "What is this?" I think you could get it because you know what a fatty acid tail looks like. It's just carbon after carbon after carbon in a long line. So
Wait, how is those 2 different, like the chain alcohol and the fatty acid?
a fatty acid chain always has the C double bond O at the end, and this one doesn't. That's about the only way. That's why they call it an acid, because it has an acid group at the end.
Okay.
You often see waxes covering fruits for protection to keep them ripe longer. And you see wax in a honeybee hive, covering the hive to protect it. Waxes are found a lot in nature because they're waterproof. Keep things waterproof. So those are lipids. We good with lipids?
We good with lipids.
Let's go on to proteins.
Protein.
Oh yeah.
Proteins.
Oh no, oh no, oh no. Oh yeah.
Or proteins. You ever heard it
Protons.
called protein? Protein.
Proton.
I've heard a lot of Englishmen call it proteins.
Like they call
Proteins.
aluminium.
I can't do an English accent, but anyway.
Have you heard that before?
What?
That how they say aluminum, aluminium.
Aluminium, yeah.
Yeah, that's
Yeah.
cool.
They pronounce more of the, we kind of run the vowels together and they pronounce it.
Interesting.
Like that's what like Harry says aluminum.
Okay. Proteins are made of individual units that I have up here on the board that I've represented as little circles. And the individual units are called amino acids. Proteins are made up of amino acids. And let me show you what an amino acid looks like. Oh!
Uh-oh.
Here's one. This is page 46, if you're wondering, at the bottom. There's an amino acid. So you have to understand here that this, hardly anybody's looking. This is this. Can you make that connection?
Mm-hmm.
So what each one of these circles has is a carbon in the middle, an amino group on this side, that's one of the functional groups we talked about yesterday, an acid group on this side, C double bond O, OH, that's an acid group. That's why they call it an amino acid. And very importantly, an R group hanging down from the center carbon. What is an R group?
Wait on.
It's a variable.
Yeah.
It can be one of 20 different things. There are 20 different types of R groups.
Let's make it J, because there's no J element.
Now you're probably sitting there going, Mr. Willis, do you have some kind of diagram showing me the 20 different R groups? And I would say, yes. Here it is. The shaded regions, notice the shaded regions. This is in your book on page 47. And by the way, if you fail the AP biology test and have to take this in college, you'll probably have to memorize all the different R groups. So
Don't
That's
fail.
not gonna happen.
make sure you pass. Cause I had to do it, and it was kind of a waste of time. We didn't have AP biology when I was in school, or obviously I would have passed it.
Uh-huh.
But we still have to memorize
You,
these now.
you would have gotten a 6.
Huh?
We still have to memorize.
No, you don't have to memorize these. You do not.
We'll hit
But-
them on the AP exam.
No.
Okay, good.
This is just showing you what they look like. And giving you an idea that, first of all, there's 20 different amino acids. Notice they're exactly the same, every one of them, except for the R group. You notice that?
Is this the same R group as what we were talking about yesterday?
No, it's different.
What was what we were
R just means variable. And so yesterday there were different variables than today. But look at this top box are hydrophobic R groups. Do you know what hydrophobic means?
Yeah.
Afraid of water.
Afraid of water. So all of these R groups do not like water, and they will move away as far away from water as they can. The middle one, all of these are hydrophilic R groups. They love water. They're in love with water. They want to marry water. And they will go toward water. And these are ionized R groups. That means their R groups have some kind of charge to it, some kind of electrical charge. And if the electrical charges are the same, they'll repel each other. And if they're different, they'll attract each other. Okay? So what? Who cares? Well, the amino acids will bond with one another. We can remove an OH from this acid group and an H from that amino group and bond them together by what type of reaction? Do you remember what the name of that was when we removed water?
Oh,
Oh,
dehydration.
Dehydration reaction. There it is right there. And we can form a new molecule that has two amino acids hooked together. Watch, I'll do it over here. Watch this. You ready? It's exciting. Boop!
Whoa.
That's ridiculous.
You want me to do it again?
Yes,
Just for those of
please.
y'all who missed it, I know. Here we go. You ready? Da!
That was a weird noise.
Now they're bonded together.
Yo, where's the dad?
And there's a name, y'all. There's a name to the bond between the two. It's called a peptide bond. A peptide bond is this bond between this carbon and that nitrogen, and it joins two amino acids together. Let's make some more peptide bonds.
Yeah, let's do it.
Doop.
You. Woo.
Pew. Bah. Whoosh.
No.
Should have done capacity.
I don't know what the last one was. I couldn't think of any
Step
more
Brothers.
sound effects.
Bah, bam, bah. Bah.
Check this out. Wait.
It's a good video.
Now we have a bunch of amino acids connected together in a line. You know what we have?
We have a
Polyamino.
We have the beginnings of a protein. We don't have a protein yet, but we're on our way.
Looks like a caterpillar.
diamond.
Now, do you notice that this string of amino acids looks a little like this string of beads they have up here?
Yes.
Yeah.
We call a string of amino acids the primary structure of a protein. You see the word primary structure there? That's a string of amino acids. And it could be several hundred amino acids long. It could be 1,000 amino acids long. The order of the amino acids determines what protein it is. You could imagine there's trillions and trillions of different types of proteins, because you can have trillions and trillions of combinations of the 20 types of amino acids. Right?
Mm-hmm.
Now, luckily, I have a chain right here. Huh?
Hey.
Pretty good, huh? It took most of one Friday night to make that. There's a string of amino acids, and we call the string of amino acids the primary structure of a protein. Now, that string of amino acids can curl around or can fold on itself. And if the string of amino acids curls around in a curlicue, like a pig's tail, we call that an alpha helix. That string, imagine this string right here, curling around on itself. We call that an alpha helix. The string can form an alpha helix. Or the string can kind of go back and forth on itself and form a flat sheet that we call a beta sheet, which kind of goes like this. If you took the string of amino acids and just made it go up and down like that for a while, that's a beta sheet. And if we made it go curlicue like this, that's an alpha helix.
Alpha.
And we call the alpha helix and the beta sheet the secondary structure of the protein. So we're going to take that long strand and we're going to wind it or fold it over. And that leads us to the tertiary structure of a protein. That's this long strand. In some places, notice in some places it's coiled up in alpha helixes, and then in some places it flattens out into beta sheets. So that single long strand will form alpha helixes in some places and beta sheets in others.
Determining on the protein, right?
What's that?
Determining on the protein.
Yes, this is going to determine the final protein.
Okay.
Is that what you meant?
Like two different proteins would look different.
Yeah, a different protein would fold in different places and wind in different places. Uh-huh.
Okay.
And that's determined by the order of these.
Are the lengths different? Like the length of it?
The lengths can be different, yeah. Some proteins are 1,000 amino acids long and some are only 50 amino acids long. So we call that the tertiary structure. And I want you to notice something in these tertiary structures. You see that lightning bolt area? It's called a disulfide bond. And what that is, it's a bond between two R groups that have sulfur. And I'm going to go back here to this picture here. Do you see that cysteine has a sulfur at the end of it?
Yes.
Hanging off this R group has a little sulfur there. You see that?
Yeah.
So if in the final structure, after this thing starts folding up, if there's two cysteines near each other, they'll form a disulfide bond that's really strong, that holds the tertiary structure together. And keeps the protein from coming apart. So really what a protein is this chain of amino acids in helixes and sheets all folded up. And often, very often, there's more than one chain. Here I bring in a second chain. Y'all check this out. I'm bringing in a second chain.
The second other Friday?
Yeah, this one's falling apart. This is older, and a lot of the things are falling off. But anyway, if you fold this chain up, and here's the first chain, and you put those together, you now have the quaternary structure of the protein, and that's the final structure.
Whoa.
Several chains, in this case 4 different chains, put together into one. That's a protein.
And that's finally a protein?
That's finally a protein. Many proteins are quaternary structures. Some proteins never get to the quaternary structure. They're just a single tertiary structure.
And that's what's in meat or in.
That's right. And steak's got a lot of proteins. Rice has a lot of proteins. Eggs have a lot of proteins. Beans. The proteins are used for different things in cells.
Bugs.
Cells can use proteins as doorways to let stuff in and out. Cells can use proteins as skeleton to help hold the shape of the cell. Scales. Cells can use proteins for movement. Some proteins do like this all day. That's their job. And it helps the cell move. In sperm cells, there are proteins in the tail that do this all day. Like that. They rub against each other, and that causes the tail to wag of a sperm.
Oh my gosh.
So proteins are very important. Oh, and proteins can be enzymes. You know what enzymes are? Enzymes are proteins that do work. They march into work in somewhere in the cell, and they grab things and move them, or put them together. They spend all day putting stuff together, and that's all they do. Or take stuff apart. The ones that take stuff apart probably enjoy that more. And that's all they do. They grab stuff and take it apart. There are proteins that can take apart 100,000 molecules per second. There are proteins that can work that fast. So they work a lot faster than y'all. Y'all are sitting here like this. And they're in there doing 100,000 per second. You want to see a protein?
Yeah.
On a computer drawing of a protein. This one's one of my favorite proteins. It's called bovine pancreatic trypsin inhibitor.
Computers can do that?
No, just that.
Was that in a cow?
Yeah.
Bovine pancreatic trypsin inhibitor is used to illustrate the kinetic nature of biological molecules. Changes are at the picosecond level. Note the behavior of the yellow water molecules.
See how the protein kind of vibrates around?
Mm-hmm.
You see all the amino acids there? Isn't that cool? That's bovine pancreatic trypsin inhibitor.
Which one was
That's what I'm going to name my first kid. Bovine pancreatic trypsin inhibitor Willis.
That kid might not like you.
Can you do that one again? Because I
Oh, which my parents
Say it
named me
again?
that.
yeah, which one was
Here we go.
One
Wait.
floating off.
the orange?
Wait.
Bovine pancreatic trypsin inhibitor is used to illustrate the kinetic nature of biological molecules.
That's water.
Changes are at the
Doesn't
picosecond
look
level.
yellow.
Note the behavior of the yellow water molecules.
They aren't really yellow.
They're kind of
Orange.
orange.
Yeah.
Well, then what's the protein?
That's the protein, the big thing.
That.
See, it looks like a big glob like this.
Is that water coming out from the dye or the
I don't know why they put water in that picture.
the dehydration thing?
Could be.
They put some water in their protein.
Could be a dehydration synthesis joined them up. Now this is my girlfriend.
Yep.
And what this shows is that hair is a protein. And hair is alpha helixes. This is everybody's hair now. It's alpha helixes, and you can see they're kind of wound around one another.
Is it helixes or helixi?
Helixi, I don't know. Helices. It's helices.
Helices.
And of course, you know, she came out like that, and I was like, you're going to have to change your hair if we're going out tonight. And so she changed her hair. And what you can do with the protein is, if you're going to, anytime you heat a protein, remember heat causes molecules to move faster? Do you remember that?
Yes.
So if you take this protein and you heat it, the protein starts doing this and will eventually fly apart. We call that denaturing the protein.
Denaturing.
And so the protein will come apart, and then when it comes back together, when it cools off, it'll come back together in the shape of, say, the curling iron, if you got a curling iron around it. So you heat it and then let it come back together, and it'll take on a new shape. That's how curling irons work. That's why they have to be hot.
Why are some like already,
Already curly?
Yeah.
Because they already have this structure. You're born with this structure, and then if you want to straighten them out, you got to heat them and straighten. So it's the same deal, only backwards.
Well, when they can like chemically straighten your hair.
I don't know how that works, but it might have something to do with the proteins. Have you ever taken an egg and you crack it and it's got all that gooey stuff and it's clear, it looks like snot, and you're like, I don't really want to eat this. And then it goes in the pan, and then you heat the pan, and then it goes from clear snot to like white, and you can't see through it. What's happening is, that's mostly protein. And the heat of the pan denatures the protein and changes its configuration from something that lets light through, that's clear, to something that's shaken in such a way that light won't go through it.
Is the protein still in it?
The protein is still in it. It's just been, it used to be one configuration, and then when it gets heated up, it changes to a different configuration that's no longer translucent, that doesn't let light through.
Why do some people drink raw eggs?
Just
Does that have to do with anything?
no, they
It
just
does.
It's a lot
tough. You know, it's in the movie Rocky.
It's a
So
lot. It's a lot of protein.
they thought, let's do that. Oh wait, let's see what the video is.
This familiar gelatin dessert actually is a good example of the process of coagulation of proteins into a three-dimensional latticework that entraps water molecules to produce a semi-solid gel. This animation explains the physical chemistry behind the process. Proteins are synthesized by polymerizing amino acids. The polymerization occurs.
Okay, this seems really bad.
It's really long.
Let's speed it up. Oh, there's the egg.
Go back.
Hold on, let's see what it says about the egg.
Go back.
Why do we say that?
There.
Stop.
Recruited to this large insoluble mass in a randomly organized structural framework that contains entrapped water molecules. One example of the consequences of unfolding and reassociating protein molecules is coagulation of egg white. Frying an egg is no more complicated than denaturing the egg white protein. The assembly of irreversibly denatured protein molecules results in formation of a solid gel. The gel entraps water molecules inside the white into a semi-solid structure which holds its shape under normal conditions. Other examples of denatured protein assembling into three-dimensional structures include the baking of yeast-risen bread.
That wasn't very good, was it? Spider webs. Spider webs are beta sheet after beta sheet after beta sheet. Can you see how those are beta sheets there?
Mm-hmm.
Yeah. And they're very strong, and they're protein though. They're made solely of protein.
So if you eat it, you'll have a lot of protein.
Ew.
Yummy.
Yeah, theoretically you could
So
probably.
if you were like
Sticky,
starving
like-
and you were like in the woods, like
You could
lost-
probably eat spider webs. If it didn't have poison, I don't know, it might have poisons on the web. that the spider puts on.
In addition to carbohydrates and lipids, the bodies of all living things contain another important class of compounds called proteins. Proteins are made up of chains of simple molecules called amino acids. There are some 24 different kinds of amino acid molecules. Any of these different units may become joined together to form a protein, and they may be joined in any order. The way a protein functions in a cell is determined by the kinds of amino acids it contains and the particular order that they appear in the protein chain. Most proteins are extremely large molecules.
Okay, that's bad too. Sorry. Anybody see a bunch of these little things laying around? On a desk, maybe? I've lost them. Unbelievable.
Can I go to the bathroom?
Yep. Okay, I'm going to hand these out. These are called nucleotides. Everybody gets a nucleotide. Don't say, Mr. Willis wouldn't give me a nucleotide. That's just not true.
They're all the same.
I'm giving you one right now. That's what we're going
Thank
to
you.
talk about. We're going to
Awesome.
talk about if they're all the
Mine are
same.
the best.
Pass them back.
Three.
Take one, pass it back.
Oh.
Fair.
Oops. Oop.
I only got one.
Everybody should have one.
Well, Hannah. Pass me that.
Oh, here they are.
There they are.
There it is.
Now, nucleotides are the monomers that make up nucleic acids.
Oh, so we're going to take
Yeah, we're going to nucleic acids now. This is the last thing. You're saying, thank God. Finally, Mr. Willis.
Yeah.
Stop talking. Up here.
In history.
Nucleic acids.
Okay.
Nucleic acids are made up of these. Everybody's holding one. It's called a nucleotide.
Nucleotide.
Nucleotide. You are holding one nucleotide.
Whoa.
I feel special.
It's impressive, isn't it?
It's very impressive. It's a big nucleotide.
Now, do you notice that the nucleotide has 3 parts?
Yes.
The 3 parts are
Dextrose.
a sugar,
Quinine.
a phosphate, and a nitrogen base.
Chicken?
Sorry.
A sugar, a phosphate, and a nitrogen base.
DX.
Now, the sugar has a name. It's called deoxyribose.
Oh.
That's where the D comes from in DNA. When they say DNA, they're talking about deoxyribonucleic acid, which the D comes from the name of this sugar. This is, when I say sugar, what I mean is it's a 5-carbon sugar, just like we studied yesterday. It's one of these. It's a monosaccharide. Only it's got 5 carbons instead of 6. So that's the sugar part.
Yeah.
Now, sticking down at the bottom is phosphoric acid, which is also known as phosphate. If you ever see in biology, if you ever see something ending with 8, you can also call it ic acid. 8 and ic acid are the same thing. Nitrate, what's another word for nitrate?
Nitric acid.
Nitric acid. Do you see? Now, what we're worried about mostly is the nitrogen base. The nitrogen base here is one of 4 different things. You might want to compare it to someone sitting near you. You probably have a different one than them. The 4 kinds are guanine,
Guanine's coolest.
cytosine, thymine, or adenine.
Adenine.
No, guanine.
The nitrogen base could be one of 4 different things.
What's circle on the list?
And we'll use just the first letter to come up with the DNA code. Have you ever heard of G's and C's and A's and T's as making up the DNA code? Have you ever heard that?
No.
Didn't do that in life science?
We didn't do
On to
anything.
Mrs. Rivers.
We didn't do anything in life science.
I don't remember any.
G's and C's and A's and T's. And let me show you how these things will connect to each other, because it's real cool. It's like a puzzle. Watch this. Put one there. Watch this. See this one? Watch this. Bloop. Turn it upside down.
Uh-oh.
Click.
It clicked.
How about up here? Take another one. You got to get the right kind. Turn it upside down. Click. And you can start building a molecule that looks like a ladder.
It's nifty code.
It is nifty. And if this molecule gets big enough, it'll start to take on a shape that twists around like this. This is a small portion of a segment of DNA. And this right here, that's a sugar, that's a phosphate, that's a nitrogen base. That's one nucleotide right there. And you can see how many nucleotides it takes to make up this molecule. And in actuality, in your cells, one DNA molecule has 6 billion nucleotides.
It's a lot.
So if you blew it up to this size, it would go all the way around the world. That's how long it is. It's a long chain molecule. It's one molecule. It's a single molecule. Actually, it's broken up into chromosomes. We'll talk about that later. But it's still really long. The point is, it's still really long.
Don't if you like structured DNA, like as thin as it goes, it'll reach the moon. Or something.
Yeah, but it's all folded up.
Yeah.
It's all folded up. I don't think the moon, no, I don't think that's right. But it would be long. And if you blew it up to that size, it'd be really long. But, maybe if you take all the DNA in every cell. That's probably what you're thinking of. Yeah, probably would, yeah. Now, where's the code? The purpose of a nucleic acid is to carry a code. This carries the code of life in here somewhere. What is the code of life? Well, if you read the nitrogen base, if you go down the ladder and read each nitrogen base, I will read G there, A there, G again, T, A, and if this continued down, I might read more letters, C, C, A, G, T, A, and on and on and on. And what does that spell? Well, of course, it spells gag-tac, ag-tac. Gag-tac, ag-tac. What does gag-tac, ag-tac mean? It means blue eyes for this guy, and make him a little short and give him a big afro and make him one of the best athletes in Frederica history. And there you go. That's the DNA code. So read about those. Do the homework sheet. Identify all those molecules. It's the rest of chapter 3.